All right, we're beginning our final discussion on columns. So these are axial members under compression. As you remember, concrete's not so great in tension, so we skipped right over that. The only actually loaded loading that we take into account is compression. And it also incorporates axial and moment. So we're going to talk about tied and spiral columns. We're going to draw an interaction diagram that shows the relationship between compression and flexural strength. And then design a short column using interaction diagram design aids. So columns, like I said, if we're talking about the loading of a column, columns generally have two loadings. One, axial compression, usually compression, I'd say. That's their main loading, but then they can also have bending or flexure. In terms of the reinforcement that you find in columns, you'll have your longitudinal bars, so along the length. And then you'll have ties or spirals similar to your shear reinforcement in beams, right? So there's tied versus spiral columns. On the left, we have our tied columns, which have discrete ties, right? Little hoops. Both ties and your spirals provide confinement. Spirals are going to be better at it. If you're looking at the tied column, let's say we apply an axial load. If you apply an axial load, what kind of deformation do you expect? Do you expect maybe a little bit of buckling, or at least, right? It's going to bump out a little bit. And with the ties, you have the space to do that between those ties. Ties are used in 95% of buildings. In non-seismic regions. Now, if we go to our spiral columns, spirals are generally going to be closer together, and you see they're right at a diagonal because it spirals up. So if you apply an axial load, that spiral tie is actually going to provide some confinement of your concrete core. It's not going to allow the same type of deflection or buckling that the tied column would allow. So the concrete core, we're going to say the spirals provide confinement more so than the ties would. So now your concrete core is actually in triaxial compression. The tied column doesn't provide that same type of triaxial compression. As a result, when concrete is in compression, in triaxial compression, it results in a stronger column. It's also more ductile. If you look at this graph over here, we have our tied column. As you shorten it due to the axial load, it has a peak and then comes down because you're going to eventually cause tensile stresses in here where it's kind of buckling and cracking and you fail. For the spiral column, you start to go up here, eventually the shell spalls, which means the shell being this outside. Spalling means when the concrete falls off, becomes disconnected to the rest of the concrete. Spalling. The shell spalls, so the outside the spiral reinforcement breaks off, but the inside remains because it's in that lovely triaxial compression, and you're allowed to have more shortening. You apply more load, it shortens more until your spiral eventually breaks. So that's what I mean by more ductile, right? The tied column is basically, it looks like it's pretty much elastic breaks, whereas the spiral column is elastic and then some plasticity with ductility, and then it eventually, the spiral breaks. And that would be at very high stress that happens. Because of that ductility, a spiral column is used for high loads. and seismic regions. So let's look at our axial strength. Pure axial, right? That means we have an axial load that goes right through the center. Right. Check it out, straight edge. Right, we go right through the center line for our axial load. That axial load causes a deflection, delta, which is equal to the strain times the length of your column. This is the strain that causes stresses in your concrete and your steel. So we have a pure axial load. The force in your column, P, is equal to the force in your concrete plus the force in your steel. And we're going to assume that our concrete and steel are buddies and they stay together and that they're going to fail. Failure of your column occurs when the two things happen at the same time. When one, your concrete reaches its failure strength as a column loaded in compression. So your column is equal, your AC, that's your area of your concrete, times, and I'm going to call this F double prime C. AC is your area of concrete. And your F double prime C is strength of concrete loaded as a column. Now, why isn't this just the compressive strength? Because this is also going to take into account the potential for buckling and all that. It's not just pure compression. F double prime C is equal to some factor K3 times F prime C. That's our usual compressive strength, right? F prime C. And K3 is equal to 0.85 based on published tests. So it's kind of like that beta 1.85 F prime C that you use when you're making your Whitney stress block from a parabolic distribution to a even distribution. Kind of think it like that. So we're going to rewrite that into K3 F prime C times AC, or 0.85 F prime C AC. So I said failure occurs when. I wrote a number 1. I probably need to write a number 2. First one talks about my steel, or my, spoiler alert. First one talks about my concrete, so the second one's going to talk about my steel. Failure of my steel is when I reach the yield of my area of steel. These are probably more familiar numbers, right? That's my yield strength. Of my steel. Longitudinal steel. Oh, I'm just going to put AST is your area of steel. It's going to be probably going to be your longitudinal, because you don't always have the ties. So my axial load capacity, if I want to write that, I'm going to call that P naught is equal to 0.85 F prime C. My area of concrete is going to be my gross cross-sectional area minus my area of steel plus yield times my area of steel. So that's pure axial loading. So pure axial loading is when we have a concentric load, right? When my load occurs right at the center. This is concentric. Loading, where your center line and the vector upon which the load are exactly lined up. So that's pure axial. But what happens if my load is off a little bit, right? Now my load P is off by a distance E. It's not directly lined up with the center line. This is called eccentric loading. And now I have a force times the distance, P times E. I'm going to have a moment. I need a moment, okay? It's giving me a moment. That moment is P times E. You also still have your also still have your load. That moment, right? We got tension on one side, compression on the other side. That moment is now causing tension and compression. We're going to call it stress. there's a stress distribution due to that moment. If this were a homogeneous elastic column, can I write that any worse? Okay. Homogeneous. Homogeneous means it's all the same material, which we don't have, but let's pretend, right? Because we have concrete and steel. And let's say it's elastic. Well, we know concrete isn't elastic. It doesn't really have the same behavior in tension and compression, right? So for a homogeneous elastic column where my failure in tension is equal to my failure in compression, that is failure stress in tension FTU equals my failure stress in compression let's say I have a perfect same material throughout, it's elastic, it fails the same in tension as it does in compression. Well, now if we look at, let's say we look at this side right here. Compressive failure occurs when my stress due to that axial load, P, plus the stress due to my moment equals my failure stress in compression. Right? If I have an axial load stress and a moment compressive stress due to the moment, they're going to add together, right? We're going to use our superposition here. And that's going to fail when it reaches the failure stress associated with compressive failure, FCO. What is my equation for axial stress? That's my force over my area. My stress due to my moment is my over I. You might have seen it as MC over I. Y is the distance from the centroid of the section, right? Y would be the centroid of the section to any distance. And that's going to be equal to FCU. If I divide both sides by FCU, P over FCUA plus MY. Y is not a subscript. Might look like it there, but it's supposed to be M times Y, right, over FCUI is equal to 1. So when those two values, P over FCUA plus MY over FCUI equal 1, we're going to have a compressive failure. Similarly, tension on the other side. So we're going to use this equation down here to start to develop an interaction diagram. I'll show you what I mean by that on the next page. This is my P over FCUA, MY over FCUI equal to 1. If I look at FCUA, that would be my maximum allowable stress axial component, or axial force, sorry, P max. All right, remember, we're not talking about concrete right now. We're talking about a homogeneous, elastic, nice thing. Nice material. We're not talking about reinforced concrete. So if I take my compressive stress, my stress associated with failure and compression, multiply it by my area, that's the maximum allowable force that I could have if I only had axial force. If I look at this, right, stress equals, maybe if you do a little off to the side, right, stress equals M Y over I. If I rearrange that and go M equals the stress associated with compressive failure times my moment of inertia over Y, that would be my maximum moment. Right? Stress associated with failure times I over the distance to that extreme compression fiber from the centroid. So if I rewrite that equation up at the top, P over P max plus M over M max equals 1. is what is graphed on the other side. Now remember, this is a homogeneous elastic material that fails the same in compression as it does in tension. So let's see, if P equals 0, then I will fail in pure, I will have pure bending. If I look along this equation, so this is an interaction diagram, okay? I guess I should have talked about this. This is an interaction diagram where we have moment along the x-axis and axial load, compression or tension, along the y-axis. If my P is 0, I have no axial load, I'm along this line. I'm in pure bending. And I will fail when I apply the maximum moment associated with FCU times I over Y. Right? When M equals M max, if I take out, let me see, I might draw this a little more. So if I have pure bending, if P equals 0, P over P max plus M over M max equals 1. Now this is 0. So I fail when M equals M max, or M over M max equals 1, plus or minus 1, because it could happen either way. There's a plus or minus if you look at this interaction diagram, because one is counterclockwise and one is clockwise, associated with tension and compression. Actually, that's not true. That's the P, is tension and compression. But that's just counterclockwise or clockwise. Right? You would fail the similar that as that. Remember, we're talking about a homogeneous thing. So I can apply a load, right? It's fine until, oh, now I've reached my maximum moment. I can apply a moment until I reach my maximum moment, provided I have no axial load. Let's look at if M equals 0. And now I'm in a pure axial state. So I don't deviate off of my Y. This is pure axial. Right. P over P max plus M over M max 1. Let's see. This is now 0. Fail when P equals P max, or P over P max. I should say M. Equals, and we're going to say plus or minus 1 because this is a magical material that fails. Not magical, they exist. It's like steel, but it is not concrete. It's a material that is wonderful and fails exactly the same way in compression as it does in tension. It exists. It's not hard to find, but it is not concrete. Right? So again, I'm like, I can apply any type of axial load, but as soon as I hit my axial capacity, I fail. Now, what this interaction diagram tells me is that the lines drawn between, this is the failure surface, as they would say. You might hear this if you take some more like geotech. This is called the failure surface. You can apply any combination of moment and axial load, like here, and as long as it's within this rhombus, my 5-year-old is learning shapes, that she would call that a rhombus. As long as it is within that surface, that doesn't fail. But as soon as it hits the surface, fail. Obviously, if it's outside the surface, it fails as well. As long as you are within this little interaction diagram that describes the relationship between how it performs under axial load and bending, as long as you're within that surface, you're fine. The minute you hit that or go out of it, now you've failed. I guess if you're right on the surface, you're like right at the cusp of failing. Something else to note is above, when P is positive, this fails by compression. Sorry, governed by compression. By axial compression. If you go P negative, now you're governed by axial tension. This point right here is going to be called balanced. We're going to talk about that on the next slide. So this is going to be a good point to, we're going to keep that in mind. So, up until now, let's remember FCU is equal to negative FTU, or they're equal to each other, right? Now, up until this point, we've been talking about a material that fails its compression the same it fails in tension. So now let's look at some other interaction diagrams. What if I have a material that has no tensile strength? Well, now I've moved my interaction diagram up. From the other one, right? Before it was like that. Now it's not going to have that. You're still going to have the same shape. You've just decreased your y-axis extents. We're going to look at points D and B. These are called balanced failure. And a balanced failure is when your tensile and compressive resistance of your material is reached simultaneously on opposite edges. So we still have the same shape. We don't have any tensile strength. We're going to talk about this balance failure. If you remember when we talked about the balanced conditions, from beams, was when your force balanced was when your strain you reached your concrete compressive strain when you reached your yield strain in your steel. If we look at the next interaction diagram, now instead of having the same compressive strength and tension or none, we're going to have half. As a result, your P over P max can equal negative 0.5. Here, on the tension side, it's 0. We can reach full compression, stress, FCU 1 on the top, right? But only half the same. It has half the capacity in tension that it does in compression, is what this is saying. When we had no tensile strength, we had to move that to 0. When we have half the tensile strength, or the tensile strength is half the compression, we can have half the capacity. 1 and 0.5. This right here on the right side, this is more similar to concrete, where we have some tensile strength, but it's much lower. So we're gonna, our interaction diagrams for reinforced concrete are gonna look more like the right side, with the exception of it's not elastic. So no straight lines. Here they assume a linear relationship because it's elastic between the failure points or the determined points. It's not failure because, well, I guess it is, but because concrete is not elastic, it's gonna be more like that. So these are interaction diagrams. This is how we are going to design columns. Columns will not be designed purely on axial load. We're going to assume, or we're going to draw interaction diagrams so that we can design them incorporating potential moments. I'm going to stop right there. Go back and look if you need to understand this a little bit better. But again, this is the failure surface. If you are within it, you are fine. If you are outside of it, not fine. Okay? And I will pause there and start the next one.